So let's jump back to the first part of Simon's overview now, so the front end. So I'm going to talk a little bit more about the front end. I'm going to talk about the front end at training time rather than just synthesis time. And specifically, I'm going to talk about...
Could you
yeah.
holding the microphone a bit closer?
Is that better like that? Is that a bit better? Is that okay at the back? Yeah? Okay. So yeah, I'm going to talk about the front end at training time, and I'm going to get a little bit closer to the tools that we like to use for this and the implementation. So as Simon was saying, the conventional front end is this pipeline of different submodules. And as Simon pointed out, these are all individually learned from data or compiled through expert knowledge. And as Simon pointed out as well, this conventional approach to building a front end is expensive. So Simon mentioned to train LTS, for example, you need a lexicon. To compile a decent lexicon, you may be looking at 2 person years, which is a lot of time and expense. To take another one of those modules, to train a part of speech tagger, you might need 1 million tokens of text, for example, manually tagged. So collecting the data to train these modules or the expertise to write them is an expensive task. So when focusing on the front end, I'm going to look at an approach that tries to bypass a lot of this expense. I mean, if you have a front end for your target language, that's fine. So if you've got, if you're working in a language that has a front end implemented in Festival or Mary Teaches or eSpeak or any number of other open source systems, that's fine. But what do you do when your language hasn't been tackled before? So what can we do just with some text and speech data? What can we do without all the labeling? And so the toolkit I'm going to talk about now specifically is what we call Ossian. And you can find it here. That's a slightly old slide. There's been an update there with a pointer to the GitHub repository, where you'll find it alongside Merlin. And this toolkit is the product of the last few years of work of trying to do speech synthesis in languages where we don't have conventional resources and we can't rely on conventional expertise. So minimally, the tools expect as input for training speech and text aligned at the sentence or perhaps the paragraph level. And ultimately, the aim of the tool is to try and exploit any other resources you can put into it in a seamless way. Although today I'm just going to talk about the most naive approach with the minimal resource scenario. So this toolkit supplies front-end modules, and also it kind of acts as a glue for incorporating them with neural nets trained with Merlin. So, as a running example, I'll take a target language that we became interested in last year and we started working on a little bit, so Swahili. And I'll show you kind of the first approach we followed to building a voice in this language. We've started adding kind of expertise and annotation, but this is the first thing we did and it gave quite reasonable results. And I'll point out some of the ideas that we try and use to manage with as little annotation as possible. I'm going to look at each of these modules from a conventional front end and say how we try and replace them essentially in this more naive approach. So the tools that we use expect as input, as I said before, speech and text aligned at maybe the sentence level. So like this is a sample of Swahili text and an image of a speech waveform corresponding to it. We require that the text should be UTF-8 encoded, or in some encoding where we know how to get to Unicode, which is very useful, as I'll point out. So this is just a little excerpt, or two excerpts from the Unicode character table, which gives us things like the classes of character. So the codes there that you can see down on the right-hand column kind of let you know whether a character represents punctuation or a letter or a space or and various other information. And it gives us ASCII representations of letter names, which is quite handy implementationally, and also we can use it in several ways, as I'll allude to later. So given this data, the first step of training a voice is to get this data into an XML tree per sentence. So as our utterance structure, we encode our utterance structure as XML. So we're assuming that the tree structure of an XML document is adequate to handle the sort of hierarchical relations we'd like to model in TTS. If you compare it with other front ends, it's kind of a simplification. So Festival is much less restricted in the sort of hierarchies you can represent, but we find it's adequate for most of the problems we see. And as much as possible, we like to rely on widely used general solutions. So XML has ways of querying structures called XPath, which I'll come to later. So people can, in theory, use our tools having become familiar with manipulating XML structures in a non-TTS context. Oh, sorry. Wrong button. Right, so let's just walk through a few of these conventional front-end modules one by one and see how we try and replace some of their functionality. So the first step is tokenization. Here we rely on Unicode, on the character properties, which I referred to before. So this regular expression you can see has worked for us on quite a number of languages, so 20, 30 languages, relatively well at splitting text into sensible strings of things like words and things between words. So essentially what this regular expression is saying is it's matching all characters which, according to the Unicode table, are letters, numbers, or marks. And then we segment incoming text with this expression and take as tokens everything matching that expression and everything occurring between matches of that expression. So we're treating both what turn out to be words and spaces as tokens. And again, we can use Unicode character properties as a way of classifying these tokens, so we have some idea of what are words and what are spaces, what are punctuation and so forth. So that does some of the work of a conventional tokenizer. I'm not going to talk here about text normalization, which is a big extra problem. But here I'm just talking about kind of the first attempt at building a voice. And this will get you quite a long way before you start to think about text normalization. So to kind of move along to the next module, in Simon's diagram at the top there, part-of-speech tags. How do we manage if we don't have a part-of-speech tagger? So assuming that we don't have a part-of-speech tagger that we can use for Swahili, what can we say about these words to characterize them in a similar way to how a part-of-speech tagger would? We can look at very simple statistics of word occurrence, and that will already tell us quite a lot. So just knowing that this word huo, we observe it very frequently in some large corpus of Swahili. We observe it frequently enough that we could guess it's a function word. This other word we observe a bit less frequently. We could hypothesize that it's a content word. So already just with looking at unigram statistics, we can learn quite a lot about words. If we look at bigram statistics, we can learn a lot richer information. So if we often see this sequence na mzozo, so mzozo often appears in this context with na to the left. that will tell us quite a lot more about it. So if you think of an English example, if we see a word house, we don't know it's part of speech, but we see it often occurs to the right of the word the. It will tell us something about that word. So it's in the class of words that often occurs to the right of the. So although we don't have labels like nouns, adjectives, and verbs, we know it's going to belong to the noun group rather than the verb group. So rather than just function-content distinctions, it's going to tell us about different types of content word. And the way we formalize this is in a vector space model. You can think of this as a way of obtaining embeddings of words. There are lots of other ways of doing it. This is one way that we've used in the past and has been very successful, but I can talk about some alternative approaches a bit later. So at the top there you can see a big matrix of count. So along the top, so the columns of this matrix correspond to types of words that we'd like to characterize, words that we observe in some big corpus of text that we'd like to characterize distributionally. And the way we do that is by counting co-occurrence just with a very narrow context. So bigram counts, left and right bigram counts. So the rows here correspond to these contexts. So we might count co-occurrence with a handful of frequent words. So in practice, 200 or 300 words, for example, gives good results. So that means that this element here that I've highlighted is just a count of the sequence of the house in this corpus. This element here is just a count of house sum in this corpus. So this column here is just a very big, noisy representation of the behavior of this word house in this big corpus. So this is big and noisy, so we'd like to compress that. And we do that with singular value decomposition, so a matrix factorization technique, whereby we obtain a compact and denoised representation of this vector of bigram counts. So you can think of the elements of this compact representation as points of words embedded in some high-dimensional space. So this is just a plot of 2 dimensions of a space learned from a corpus of Swahili words. And we'll just zoom in on a little point in the middle of that space here. So there are 2 words here highlighted which occurred in the running example, so Nzozo and Huo. So as the unigram count suggested, Huo ends up surrounded by, these are its nearest neighbors in this space, by many function words. Zozo ends up surrounded by many content words. But the fact that we've used bigram context gives us rich information. So many of the words that surround Zozo are nouns, and many of them are in fact abstract nouns, although my knowledge of Swahili doesn't let me comment much on the details. It's obviously very noisy, so there's noise in there, like you can see a London next to Huo in the function word group, but on the whole it captures enough regularities that it's useful for TTS. So how do we integrate this information into a system? So the matrix decomposition effectively gives us a lookup table. Looks a bit like this. So when we see the word Bunzozo, we can just look it up from this table and obtain a numerical representation of it. And we might have it outside the XML, or we could put it actually in the XML directly. So these numbers, in some sense, replace part of speech categories. I'll talk now about the next module in this pipeline, LTS. How do you manage without lettered sound rules? So we've gone a long way in our work just by very naively using the surface forms of words as a replacement for phones. So as a replacement of phones, we can just use, for example, letters in a word. And for the majority of the world languages, the majority of them use scripts which fall into these 3 categories, so alphabetic or alphasyllabic or abugida, or consonantal writing systems. And certainly for the first two of these, we've done we've built many systems with some success. But for all three of them, there's at least quite a consistent correspondence between sequences of graphemes and sequences of phones in a language. Obviously, this approach isn't going to work for scripts with big logographic content, so Chinese characters, but for the majority of scripts, it'll work to some extent. So you can see here an example of as segment labels, as pronunciations or stand-ins for pronunciations, we're just using the letters from this word here. And again, I've put a snippet from a Unicode character table there, just as an indication of tricks we could use to make this naive approach a little less naive with very little effort. So if you look at the ASCII descriptions there, so that's there's some lines of the table there relating to Ethiopic script. So it gives you some alphabetized forms of characters. And we've had a little success with Alpha-Slavic scripts, with Indian language scripts, just by using Unicode character table lookup and 2 or 3 rules, and you can already alphabetize those scripts essentially. But that's a little more, that's using a little bit more ingenuity than the very straightforward approach I'm proposing here. So before sending this data to an aligner to get time alignments, we also make an initial guess of where to put silences, so possible pauses or probable pauses, and we can do that just by hypothesizing that there'll probably be a pause at a punctuation and possibly at a space, white space. And given that, we can do an alignment. So at training time, we'll do an alignment with some audio, and we'll refine our initial guess about where silences probably or possibly are to saying where they actually are detected in audio. So there was actually silence detected after Khartoum there. And it'll give us timings for the position of phones and subphone states in our data. So moving along to the next kind of module in the conventional pipeline shown at the top right there. What do we do about phrasing? So quite naively again, we just treat silences as a proxy for prosodic phrase breaks. And we can add phrasing structure to our XML. I say this is naive, but it's fairly effective. Obviously, not all acoustic silences will be phrase breaks, and conversely, not all intonational phrase breaks will have an acoustic silence. But given a little filtering with minimum silence durations, it's at least quite a precise, it has quite a lot of precision. Again, that's an approach that can be refined, but as a first strategy to getting a voice working in a new language, that's what I recommend doing. And then at runtime, of course, instead of detecting silence, we'll have to predict silence. So from this data, these words and word vectors and detected silences, we can train a statistical model, so a decision tree or a neural network of some type, to predict breaks based on some lexical context. So that lets us handle phrasing to some extent. I'm just going to kind of jump forward a little bit into Shrikant's area of how to take this tree-structured information that we've produced and flatten it into context vectors that we can use as input to some neural network. So flattening this structure. And I mentioned before this XPath formalism that comes for free with XML, and that's what we've been using. So here are some 4 examples of XPath expressions that we use to extract features at each phone or at each state across an utterance. And I've given 4, but you might use 50 or 100, 200 of these. And I'll just break one of these down so you get some idea of the implementation. So this is just a graphical representation of a bit of this, a simplified version of this utterance structure. And let's just take the third XPath there, which for any given state or phone tells us the length of the current word, so the word within which that phone or state occurs in segments. So the first part of that XPath essentially jumps up to the ancestor of the current phone, which is a token, and then the second path jumps down to all segments beneath that token, and then you've got the count expression out there that just counts them. So the length of the current word in segments is 3. But Shrikant will say more about flattening these structures. Just to persuade you that this very naive approach I've outlined can actually bear fruit and give some initial good results when moving to a new language, I'll just play a few examples. So I mentioned that we started working a bit with Swahili last year. So first of all, I'll just play you a snippet of studio data that we recorded especially for TTS. This is actually the same utterance I used as a running example from the training data.
Khartoum imejitenga na mzozo huo.
So this is synthesis based on that data.
Tanzania nyuma kwa furaha duniani.
Okay, it's not perfect, but it's pretty good as a first stab at this. And based on this, we can add knowledge and improve the voice. What do we want to do what can we do if we don't want to record data? So the very first voice we built in Swahili, we built in 2 days just by scraping data from the web. So we used, in fact, Bible recordings. This is an example of that data.
Hapo mwanzo Mungu aliziumba mbingu na nchi.
And just using the naive approach I outlined.
Tanzania nyuma kwa furaha duniani.
Again, it's not brilliant, but it's not bad for a day or two's work. And when we built this first voice, we were looking around for kind of other Swahili systems out there. And the first one we came across was the one in eSpeak.
Tanzania nyuma kwa furaha duniani.
Which is obviously quite an old formant-based system. But it is the one used on the Google Translate webpage. So I guess it's even Google has to resort to using these legacy systems for less resource languages. Okay, I'll just wrap up now by saying a few words about design choices of the front end. I'll hurry up because I don't want to go behind time. So I've mentioned using letters. You can choose to use phones or some mixture. Let me just skip ahead to the various choices for word vectors. So there's lots of kind of fashionable ways of learning word vectors these days. You might want to learn them as weights within a neural network. So you can jointly learn these things with some other task. I think a more important design choice for word vectors is how you handle subword morphology. So doing some sort of, especially in morphologically rich languages where the observations of surface word types are sparse, you probably want to break stuff down more. So whether using expert morphological knowledge or some pseudo-morphological segmentation. So to improve an AI front end, you might want to add text normalization. You might want to start very conservative. It may or may not be important depending on your application, and different types of expansions might be important for your application. So I wouldn't spend a lot of time doing that until you know what the problems are in initial first voice. And again, you can experiment with adding lettered sound rules to compensate for any observed problems in your voice.